A Fibonacci heap is a special way to reorganize data, kind of like a collection of trees. Each of these trees follow a rule, similar to what we have learned about min heaps or max heaps before. Remember, these rules help us make sure that the most important values is on top. Now, in a Fibonacci heap, a tree can be a little different. It's not limited to just having two children. It could have more or sometimes none at all. And that's what makes it unique. Plus, the really cool thing is that the operations you can do on this heap are super efficient, even more than what we can do with other types of heaps like binomial or binary heaps. Anyway, why it's called a Fibonacci heap? Well, it's because of a math thing. The way these trees are built, a tree with a certain order will have at least a specific number of nodes, and that number is related to the Fibonacci sequence, which you might have heard in math class. So, when we say a tree of order n has f of n plus 2 nodes, we are talking about using Fibonacci numbers to figure out how many nodes it will have. In this case, it is the n plus 2th Fibonacci number. A Fibonacci heap has some important characteristics that make it work. It's like a group of trees, but they follow a specific rule. In each tree, the parent nodes is always smaller than its children. This helps us keep the most important value at the top. There's a special pointer that always points to the smallest value in the whole heap. So if you need the smallest value quickly, you know where to find it. This heap also keeps track of something called marked nodes. It's kind of like a note saying that a node's value was decreased. This is important for a certain operation called decrease key. Inside the Fibonacci heap, the trees don't really have a specific order like we have seen before, but each tree has a starting point called the root. This helps us keep track of all the trees in the heap. Alright, let's understand how the nodes in a Fibonacci heap are stored in memory. In a Fibonacci heap, the starting point of all the trees are connected together so that we can quickly find them. Imagine it like a chain of trees. Each parent node has its children connected to each other in a special way. It's like they are holding hands in a circle. This helps us quickly move around the children. Using this circular linked list has two cool benefits. When we want to remove a node from a tree, it's super fast and takes only a constant amount of time, like snapping your fingers. Combining or joining two lists like this is also really fast, just like that in constant time. So, this special way of connecting nodes make things much quicker when we are working with Fibonacci heaps. Alright, let's talk about how we insert elements into a Fibonacci heap. Here is how the process works step by step. First, we create a new node for the element we want to insert. We set some initial properties for this new node, like its degree, which is initially 0, parent, which is initially set to nil, meaning no parent, and child, also initially nil, and it's positioned in the circular doubly linked list, both left and right set to the nodes itself. We also mark this new node as not marked to keep track of certain operations. Now, we are going to put this new node in the heap. So, we connect it to the root list. This means it's not a child of any other node and it's at the same level as other root nodes. If the heap was empty before we inserted this node, we simply mark this new node as the minimum. If the heap wasn't empty, we compare the key of this new node with the key of the current minimum node. If the new node's key is smaller, we update the minimum to be this new node. Finally, we increase the total count of nodes in the whole heap. So that's how we insert a new element into a Fibonacci heap. We make sure to update properties and connections as needed to maintain the heap's special structure and its properties. Alright, let's talk about finding the minimum element in a Fibonacci heap. The process is actually quite simple. You see, there's a special pointer in the Fibonacci heap called the min pointer. This pointer always points to the node with the smallest value in the entire heap. So, when we want to find the minimum element, we just follow this pointer and it leads us directly to the smallest element in the heap. Think of it like a shortcut. Instead of searching through all the nodes to find the smallest one, we can just follow the min pointer and there it is. This makes finding the minimum element a really quick operation in a Fibonacci heap. So let's dive into the process of uniting two Fibonacci heaps, which is like combining them into a single heap. So here is how it's done. First, we take the roots of both heaps and simply put them together. It's like we are merging their root lists into a big root list. Then we go through this new root list and find the nodes with the smallest key. That node becomes the new minimum in the combined heap. So we update the min pointer to point to it. Think of it as bringing two heaps together and arranging their roots in a one line. Then we pick the smallest element from all these roots to be the new leader of the combined heap. In this way, we have successfully united two heaps while ensuring that the minimum element is still easily accessible through the min pointer. Alright, let's delve into one of the most crucial operations of a Fibonacci heap, the extract min operation. This is where we remove the node with the smallest value from the heap and then readjust the structure of the tree. Here is how we perform this operation. First, we delete the node that holds the minimum value in the heap. This is usually the root of one of the trees in the heap. After that, we update the min pointer. This pointer now points to the next root in the root list. Remember, the root list is like a chain of trees and this pointer helps us keep track of where the smallest element now resides. Now, we do a bit of rearranging to ensure that no two trees in the root list have the same degree, which means number of children. We create an array that's as big as the maximum degree of any tree in the heap before deletion. We then go through the root list and for each tree, we map its degree to the corresponding slot in the array. If two different trees have the same degree, we perform a union operation on those trees. This union maintains the min heap property, which means the smallest value remains at the root. So this process might sound complex, so let's break it down with an example. Imagine we have an Fibonacci heap with various trees. Next, we start by removing the minimum heap, adding its children to the root list and update the min pointer. Let's say the maximum degree in our tree is 3. So we create an array of size 4, one extra for convenience. As we traverse the trees, we map their degrees to the array. When we find trees with the same degree, like ones with 23 and 7, we combine them. Again, 7 and 17 has the same degrees, so we unite them as well. And again, 7 and 24 have the same degree as previous one, so unite them as well. Then we map the next nodes. Again, 52 and 21 have the same degree, so we unite them as well. So similarly as before, unite 21 and 18 as well. And next, we map the remaining route. So after these steps, the heap structure is readjusted and we have our new heap configuration. So in essence, the extract min operation ensures that we efficiently find the smallest value, removing it from the heap and then maintaining the structure of the heap so that the min heap property holds true. This keeps our Fibonacci heap in good shape for further operations as well. So let's look at the complexities of various operations in a Fibonacci heap. These complexities help us understand how efficient these operations are in terms of time. Insertion. When we insert an element, it's remarkably efficient. It takes constant time, denoted as big O of 1, which means the time it takes doesn't grow with the size of the heap. So adding element to the heap is very fast. Find min. Finding the smallest element is also super quick, taking constant time of big O of 1. This is because we maintaining a pointer to the smallest element in this heap. Union. Combining two heaps is also very efficient, taking big O of 1 time. This means that merging two heaps won't take much time, no matter how big they are. Extract min. Removing the smallest element, although efficient, takes a bit more of time. It's logarithmic in nature, which means big O of log n. This means that as the size of the heap grows, the time taken to extract the smallest element increases, but not too drastically. Decrease key. Reducing the value of a key takes constant time, which is big O of 1. This operation allows us to update the property of an element quickly. Delete node. Deleting a node also takes logarithmic time, which is big O of log n. So removing any node from the heap, including the smallest one, is reasonably efficient. In summary, Fibonacci heaps are designed to perform most operations very efficiently. Operations like insertion, finding the minimum, and merging heaps are lightning fast, while more complex operations like extracting the minimum or deleting a node takes a bit more time but still offer efficient performance. Let's discuss how Fibonacci heaps are used in real-world scenarios. One significant application is in improving the performance of an algorithm called Dijkstra's algorithm. This algorithm is used to find the shortest path in a graph, which has various practical applications like finding the quickest route between locations on a map. The unique properties of Fibonacci heaps makes them useful in optimizing the time complexity of this algorithm, ultimately leading to faster hand and more efficient path finding.